Okay, in this video we're going to look at weak acids in particular. I'm going to look at them in relation to what we would need to do to pass NCA. What is this? 3.4, I think, which is equilibrium of species in equilibrium in aqueous solutions. So in this video we're going to be looking specifically at weak acids. Excuse that noise. So weak acids only partially dissociates. Now, what we mean by that is they set up a dynamic equilibrium with water. So we generally use this symbol here, HA, to represent a weak acid. There's a hydrogen or proton plus the acid. The A represents the rest of the acid. It reacts with water. And when it does that, it gives its proton to water, donates it because it's an acid, and we have a dynamic equilibrium happening when we do this. So we get an A minus produced here and an H3O plus. Now this HA is our weak acid, and A minus is what we call a conjugate base. Now, interestingly, a conjugate base is actually just itself a weak base. So a weak acid also produces a weak base. If we look at a specific weak acid, so here we can look at hydrogen fluoride, we can just write it just as we did with the generic one. So HF donates its proton to water, sets up a dynamic equilibrium, so we have F minus plus H3O plus, with F minus being our conjugate base, which in itself is a weak base. Now, this leads us to write an expression where we put the products over the reactants. And when we do that, we get this expression is called Ka. Now, when we draw a Ka, the interesting thing about water is that its concentration we assume is always constant. It doesn't vary much from 100, so 1,000 over 18, which is the molar mass, 1,000 grams, molar mass is grams per mole, and this is grams per liter. Okay, so it doesn't change much from about 55.5 moles per liter. That's the concentration of water in water. Okay, so that's the concentration of H2O. So if the concentration of water doesn't change, what we do is we just ignore water and we don't write it in an equilibrium expression. So we're going to put the products over the reactants. So if I was to write the Ka for above, so the Ka for HF, it equals our products, F minus, H3O plus, over our reactants. Now, we're not going to put water in here because water is included in the constant in the Ka. So we just have on the bottom the weak acid. So conjugate base multiplied by the hydronium ion over the weak acid. Now, the value for Ka, because when this partially dissociates, only a very small amount of the conjugate base and the hydronium ion is produced at one time, so the value is usually small or very small. Okay, so the value is very small, and the smaller the Ka, the less of the weak acid, or the less of the conjugate base or the hydronium that's produced, and the weaker the acid. Oh, sorry, on the side here I could have just drawn a generic one, which would be A minus, concentration of A minus times the hydronium ion concentration over the concentration of the generic weak acid, which is HA. Now that leads us, because we have a Ka, we can also work out this thing called a pKa. Just like if we have we'll see what pKa means, but P, just so you know, is the negative log. So P equals the negative log of something. So pKa equals the negative log of the Ka. So Ka values are very small usually. So, and we're talking like numbers like about, you might have 2.3 times 10 to the negative 6, right? Now, generally, those types of numbers are difficult for a lot of people who aren't confident in maths to interpret or to find out what's bigger or smaller. So if we put it into a negative log, it gives us a number just as a couple of digits. So we can change a Ka to a pKa in the same way that we change H3O plus to pH. And that same way is we go, okay, pKa equals negative log of the Ka. Whatever the value for Ka is, we negative log it, and we get the pKa. Example. Okay, so here's an example. We have a weak acid has a Ka of 1 times 10 to the negative 13. So its pKa equals negative log, so that's not 13, that's 15. 1 times 10 is 15, 11. 1 times 10 to negative 11. So its pKa equals 11. Now that number 11 is, I say, hey, the pKa is 11. You go, oh yeah, I understand the size of that. And if I gave you another pKa of 6, you would know that 11 was bigger than 6, or that it was a weaker acid. Okay, so the bigger the number that we get for the pKa, the weaker the acid it is. That's important to know. The bigger the value, the weaker the acid. So here's another example here, but not so straightforward. So if I had, in this case, some hydrogen peroxide, now we know it's an oxidizing agent, but it can also behave as a weak acid. Now it has a very small Ka. But when I write it as a pKa, it gets to be a larger value, which is 11.65. So the larger the pKa, the more of a weak acid it is. That means that the less it dissociates, because it has a very small number, because it has hardly anything on the top. Okay, so this is a low concentration, and on the bottom we have higher concentration. That means it does not dissociate very much at all. Not very many peroxides dissociate compared to how many there are. So high concentration of this. Okay, so that is a weak acid. That's generally what it is. In my next video, I'm going to talk about how do we work out the pH of a weak acid.